Okay, so yesterday we talked about the activity series portion of this, where the evidence is given to you in a data table. We basically take metal strips and add them to, and react them with metal ions and see which one reacts. Not all reactions are useful or helpful that way. That can be broken down into that breakdown. So there's a second thing that we need to be able to create, or a second method that we need to create a table of values, or a table of redox equations. Okay. So we are going to see if my board works today. No, it doesn't want to work. That's why the mice stay in front. So I'm going to try something different today. We are comparing the strength of oxidizing and reducing agents. Mrs. Whalen would be very unhappy with me if I decided to throw my computer through a window. So our learner outcomes: compare relative strength of oxidizing and reducing agents, and comparing the spontaneity of a redox really. Now it works. Sorry. Now, when we studied our tables yesterday, we came up with two generalizations. They're basically the same generalization, just did you know that? Yeah. So the two generalizations that we talked about is, how do we compare? If we have a spontaneous reaction and we were to look at the table, we would find the oxidizing agent falls above the reducing agent on your table of half reaction. So again, spontaneous means without the extra addition, or without the addition of energy, and it often is a reaction that occurs immediately, but not necessarily. So an OA above the RA on our table, therefore we get a spontaneous reaction. If we have the OA below the reducing agent on that table, we have a non-spontaneous reaction, i.e. we don't get any products. To get products, I need to force the reaction by hooking it up to a battery or something like that. Now, as I said, sometimes it's not easy to do those tables that we did yesterday, the activity series. Notes don't want to work. Okay. So, So here's a reaction. This actually wouldn't be too bad in an activity series, i.e. doing it, working from there, but we're going to do it in our next method. Here we give you three reactions. Two of them are spontaneous, these guys, because I gave you the products, and one is a non-spontaneous, because it says no evidence of reaction. It might be a couple other ways of writing that down, but generally we're going to use the generalization from the last slide, the OA above the RA spontaneous, and for the non-spontaneous, the OA below the RA. So in two cases, we're going to arrange them using this guy, and in the other case, we'll arrange them using that case, or that I did one there. So first we have to identify the OAs and the RAs for each of the reactions. Okay, so what we have here, we've got cobalt 2 plus going to cobalt solid. Remember that 2 plus means there's two less electrons than protons. So this guy gains electrons. So since he gains electrons, is he undergoing oxidation or reduction? Reduction. Is he the OA or the RA? He is the oxidizing agent. This guy loses electrons. He is undergoing oxidation, but he is the reducing agent. Okay. Remember, oxidizing agents gain electrons, reducing agents lose electrons. So, because it's spontaneous, going back here, it's spontaneous because we have reactions. In this case, the OA is higher on the chart. So that means, I forget which one my OA was. My OA is above my RA. I don't care about the 2. Okay, I just care about the values. So when we arrange our table, CO, you're right. So this is our OA, this is our RA. We'll keep that in mind and we'll create a table from that in a minute. Here we have the copper going from 2 plus, so 2 at less electrons than protons, to copper solid. So he gains electrons. This guy happens to be, in this case, we start with cobalt solid and we end up with cobalt 2 plus. So he loses electrons. So again, here is our OA, the copper 2 plus. Here is our RA. Once again, this is a spontaneous reaction. So I would arrange this with my copper 2 plus being above my cobalt solid on my table. Now keep that in mind. We'll do the table in a minute. Now here we have a non-spontaneous reaction, and no evidence of reaction tells me this. How do we tell which one is which? Well, we can go back and we said copper 2 plus last time gained electrons. Well, that's probably the same thing that's going to be happening here. The other thing is, the only thing copper 2 plus can become is either copper solid or copper 1 in this case. And the palladium, and I do not know what the charge is on this one, so I just go look. I think it's either 2 or 4. And that doesn't help me. Out of booklet. So palladium, Pd, is a metal, so I know it's going to form some type of positive charge. In this case, we're going to form a plus. It could form a 2 plus. It didn't, because the copper was not strong enough to rip the electrons off the palladium. What we can see here is we see again, it tried to gain electrons, and this guy hung on to its electrons, but he was trying to make the copper 2 plus was trying to make the palladium lose electrons. So again, we have this trying to act as an OA, this resisting acting as an OA, or an RA, I should say. And that means my copper 2 plus falls below my palladium on my table. Okay. So we have the three things that we were working with. We know copper 2 plus as an OA will fall below palladium. We know, we're supposed to back the heck up. We knew from this one that the cobalt 2 plus was above the indium. And we know from the second reaction that the copper 2 plus was above the cobalt. Now, if I'm doing this in order, in the order that the reactions occurred, I'm going to put the cobalt 2 plus above the indium. And I have an OA column and an RA column. So I arrange that for my first guy. The cobalt solid is going to fall in the same line as the cobalt 2 plus. I must add 2 electrons to get to the cobalt solid. The indium is a 2 plus, I do believe. And the same thing here, the indium 2 plus is going to fall in the same line as the indium. So we got part of our table done. Notice I left lots of space above and below. The next thing that we had our second one, we had copper 2 plus in a spontaneous reaction with cobalt solid. So again, it must be above. And I'm just going to create the finish off the half reaction, although I will need 2 electrons. And then finally, the palladium solid as an RA was above our copper 2 plus because there was no evidence of reaction. The reducing agent did not allow the oxidizing agent to take off electrons. So I'm just going to finish off this Pd2 plus 2 electrons. Yes. So again, this is another table that we use to create the table here. And it has to do with the OA above the RA spontaneous, or the OA below the RA, non-spontaneous. Which one of those do we use? Well, it depends on what the reaction type is. So let's do this one. I'll do it in one step. Okay, I'll do it just here. Couple things. I'm going to cross this one off because it says it's not a redox reaction. Yes, there is a spontaneous or a reaction that takes place immediately, but because it's not a redox reaction, the OA and RAs don't come into it. There's no electron transfer with that one. So let's just go through. I want you guys to go through and identify in the three other reactions, identify which are the OAs and which are the RAs. Now, what I've quickly done here is I've created the products if a reaction had taken place, in that it might help you figure out which one is which. So all I'm looking at is the charges on the periodic table. Silver forms a +1, iodine forms a -1. Bromine, if it reacts by gaining electrons, forms a Br or a -1. And chlorine, if it loses electrons, we'll just go back to chlorine. So is the silver metal going to gain or lose electrons? So is it the OA or the RA? So the silver is the RA because it loses electrons. It allows the other guy to steal them. The bromine is the oxidizing agent. Silver in this case is still going to be the RA. The iodine will be the OA because, again, it's trying to form one I negative. It can't. And down here, the bromine gains electrons to become the bromide ion. So this is your oxidizing agent. And this is your reducing agent because it loses electrons. Now, just to do it on here, I'm just going to start. I've got a table. I'm going to say OA on the left-hand side, RA on the right-hand side. So here's my silver. Notice I don't start right next to the top. So where am I going to put my bromine? On the top or the or above it? On this line above it or on the line below it? Yes, above, because we have a spontaneous reaction. So the bromine goes up here. Now I'm just going to complete the table because bromine is going to form the bromide ion. I need two of them because I have two Brs over there. Hence, I need two electrons here. Silver, I'll just create that table or that half reaction too. But I only need one electron because it only loses one in that reaction. I have a bad habit. I'm going to run out of room because I didn't. So here we have the next one. We have iodine as an oxidizing agent, and there's no evidence of reaction. So here is our reducing agent. Am I going to put iodine above that one or below that one? No evidence of reaction. So the OA is below the RA. So because it's a non-spontaneous, so my iodine goes down here. And again, because it's a diatomic, it's going to form two iodide ions. And therefore I need two electrons. Now, as I said, I did run out of room. Again, we have no evidence of reaction. So our chloride reducing agent must be on the line or on a line above the bromine oxidizing agent. And there is another half reaction table that we have. And what we've done is we've taken all these. Question? No? If you have a question, ask it. I want to make sure we understand. This? That's just I don't know why I put that there. Okay. So there are four lines, just like there are four lines on this table here. I can find each one of these, and because they are on here, we can see that the chlorine is where my finger is now. The bromine is just slightly below it. The silver ion is again just slightly below the bromine. And then the iodine is way down. Well, not way down. It's just underneath. So basically in the top quarter, but in this order, chlorine, bromine, silver, ion, and iodine are all in this order. Now, they're not going to be that nice to you on a formula or a diploma. They're going to give you equations that don't actually show up on here. They show up in that booklet there. But what they've done is they've taken all these different reactions, different tables of half reactions that we've created, and they've shoved them together. So here are two hypothetical ones that have no basis in reality because they're just numbers A through F. But this table was created, and then at another time, this table was created. Now, looking at those two tables, which is the strongest oxidizing agent that's listed in those two tables? And why? Bromine, or the B in this one, is at the top, but it's second here. So your highest is your strongest oxidizing agent. It's that guy. Because he's above the strongest in the next one. And right underneath that would be our B. Okay, so what do you think's next? Already dealt with that one, and those two are gone. Which one's next? Yes. E is next. Because E is between B and A is the next one in this group. So we have to put E in there. All right, I'm going to get rid of that 2 because that doesn't need to be there. We're just forcing them together like this. And then, okay, then it's just, what do we have left? We have A, C, and D. So we're just going to put those in now. Okay, not that one, right? So that's how we've come up with this table. I had nothing to do with it. People who are smarter than I am came up with that table a long time ago. And as I said, since this table is just a smaller version of here, I've got basically 2 full, well, you can see all the different values in here for half reactions. So there's not just this amount of half reactions that we can use, but we have probably 5 times that listed in this book. That's my age, quite literally. 1969. That's how old this book is. It's also how old I am. Okay. So that's how we came up, or we scientists came up with the table of half reactions. Again, determined empirically. Theoretically, we don't know why. We don't ask you to explain why chlorine is a stronger oxidizing agent than bromine. There are some generalizations we can make. Chlorine is a smaller atom than bromine. There's not as many electrons between the nucleus and the outer electrons, that type of stuff. So there's a stronger force of attraction, but we aren't going into that theory. We are only looking at the empirical process, the empirical reasons for this. Now, there are some generalizations that we can make about this. Without having to look at the table, you should be able to tell me if something is an OA or an RA. Generally, elements, nope, never mind, nonmetals act as oxidizing agents. They have the ability to gain electrons. Also, metal ions. Methyl ion can. Now, there are some exceptions. Every metal ion can act as an oxidizing agent, but some of them also act as a reducing agent. We only have the three that we mentioned yesterday in the data booklet, but we do have to talk about those. What class of elements behave as reducing agents? These are metal elements. And non-metal ions, because they have metal elements can lose electrons to form their positive ion charges, and the non-metal ions can lose electrons to go back to their elemental forms. Now, why is it this case? Talking about our understanding from grade 10, grade 11, well, actually, probably grade 11, some grade 10 work with this. Why do nonmetals behave as oxidizing agents? Well, nonmetals behave as oxidizing agents because they have space for electrons. Oops. So remember that element, or to form an ion, an electron, or an element is either going to gain electrons to get to the nearest noble gas, in the case of the nonmetals, or it will lose electrons to get to the nearest noble gas. Okay? So, again, generally, I guess I should put something else. And generally for metals, it's easier to remove because they're far away. Generally, they are far away from the nucleus. And what the heck happened there? I don't know what happened. Non-metal ions, they have more electrons than protons. Being lazy and writing E negative for electrons and P plus for protons. But because they have more electrons than protons, these electrons are held a little more loosely than, let's say, the electrons in chlorine gas. Chloride ion holds those electrons a little more loosely, so we can remove them from that. When we start getting into the nonmetals, we have a lot more protons than corresponding metals in the same row. And because of that, the molecule, or sorry, the atom starts to get smaller. Metal ions, or metals are big, nonmetals are smaller than that, even though they have more protons and more electrons. Those electrons are hard to rip off, but they are easy to rip. They are easy to take electrons from somebody else because of their size and the number of protons. And metal ions have space to fill. Okay, so you have more protons than electrons. There's space to fill to get back to their elemental form. And because there's more protons than electrons, they have an attraction for electrons that are floating freely. Again, this is going to be, well, this last couple slides are a little more difficult because we didn't get around to, we really didn't get around to talking about intermolecular and intramolecular forces. We'll cover that as we go through this year. Are there any questions on this stuff? This is one of, like, this process of doing all this here, it is a little bit more difficult than the other stuff. Because they're two separate processes. You don't take these equations, put them into a chart. This one actually would work, but the other one would not. So you have to get through this idea. If it's spontaneous, the OA is above the RA. And I'm going to arrange that in my table. If it's non-spontaneous, the OA falls below the RA. So I now know that if I try to react indium 2 plus with palladium solid, there would be no spontaneous reaction. However, palladium 2 plus with cobalt solid, it's on my table higher. Now I can tell that it's spontaneous. I only needed to do 3 reactions instead of the 9 that I would have to do if I was to do activities here. So your homework is given to you there.